Welcome. This question says, what is the magnitude of an electric field at a point that is 3 meters from a 6 coulomb point charge? It doesn't say if the charge is positive or negative. Let's assume positive, and let's visualize to begin with. So first of all, I'm going to draw my point charge. I won't draw it quite as a point. I'll do it as a small circle, and then this is going to be 6 coulombs, and I'm going to say it's positive. And then my point of interest. My point of interest is here, and this point of interest is 3 meters away. So that is the separation between there. And what would my electric field look like? Well, at that point there would be a electric field vector, and the electric field vector would be pointing away from the positive charge, and it would have a certain size. If I'd picked a point that was closer, the electric field vector would be bigger, and so I'd have a bigger arrow. If I picked a point that was further away, the electric field vector would be, the magnitude of the electric field would be smaller, and I'd have a smaller electric field arrow. So there's my visualization. It's not asking me for the vector this time, it's asking me for the magnitude. And if I recall, I always like to recall some of my basic equations, and we know quite well that Fe is equal to Ke, the parent charge, the secondary charge, over R squared. And the electric field is the force per unit charge, so that would be the force over Q. And so we can say that our electric field magnitude is equal to Ke, the parent charge, the charge that sets up the electric field, over R squared. So this is big Q. And in books you'll see Q1, Q2, QA, QB. I like big Q and little q. It's just, don't let the actual specifics cause you grief. Just look at the form and go with the flow. So then the next thing we have to do is actually just do the math. So this is going to be E is equal to, sometimes in a test I will let my students leave Ke as part of their answer, but in this case I want them to work out the number, so it would be 9 times 10 to the 9. That's the value for Coulomb's constant. And in this case Q is going to be 6 because it's 6 coulombs, and then in this case R is going to equal 3, and we square it. So that would be 9 times 10 to the 9 times 6 over 9. So mathematically it's very easy. So E is equal to, it's going to be 6 times 10 to the 9. And then we have our units, and the units are going to be newtons per coulomb. If you think about it, the force per charge is going to be newtons per coulomb, is our answer. And just by the by, if we look at this relationship and I plot the force versus R, I get an 1 over R squared relationship. So for a given Q, big Q, and a given little q, if I change the separation, the relationship between the resulting force and the separation follows a 1 over R squared. Now, it's important to recognize that this situation only has one charge. People quite often will say, well, what's the charge at point P? And the fact is there is no charge at point P. The electric field is all about big Q and the position. But it still has a similar relationship. We have E and we have R. So if imagine taking points further and further from charge Q, again it will be a 1 over R squared relationship. So for both electrostatic force and for electric field, if I double my distance measurement, in this case between the two forces, between the two charges, and in this case between the charge and the point of interest. If I double that distance, I will get 1/4 the electric field. If I triple the distance, I would get 1/9 electric field. If I 4 times the distance, I will get 1/16 electric field. Just as if I double the distance between the charges, I will get 1/4 the force felt by either one of them. If I triple the distance, I will get 1/9 the force felt by either one. If I quadruple the distance, I will get 1/16 the force. With expressions like this that are similar but different, it's really good to spend some time comparing and contrasting them. They're both 1/r², but this one contains both the big Q and the little q that must be there to cause the force. And in terms of electric field, it's 1/r², but there's only one charge that's being considered. So there we have it.